Acids versus bases in biochemistry. In a few minutes, you'll understand pH buffers and how cells stay balanced.
Hello, welcome to Biochemistry Simplified. This is Dr. ELIC, and we're just going to continue from where we left off a while ago, and we're beginning with strong acids and bases. We've looked generally at the acid-base chemistry, and we are just moving right along to begin with the strong acids and bases. So, what is it really that is a strong acid? What is a strong acid? We want to begin by knowing exactly what strong acids means. They are acids that completely dissociate when put into water. Simply put, so strong acid are acids, as the case may be, they are acids that completely dissociates, okay, the acids that completely dissociate when put into water. That is, for example, of a strong acid, take for example, you had to, okay, that completely dissociates when put into water. Take for example, HCl, which is your hydrochloric acid, and introduced into water, it completely dissociates. First, it turns into HCl in aqueous solution. Why? Because it has been introduced to water. On its own, it is not an aqueous solution. It is a strong acid. So when it becomes HCl aqueous that's floating around in water, it completely dissociates into the hydrogen plus, which is your proton, and your Cl minus. So we want to note that HCl on its own are solvents. They are solutions on their own. They become acids when they are put into water, and they become solutions, which eventually dissociates to form H plus, which is your proton, and your Cl minus. So I like to put that down. HCl on its own is worthy of note. On its own are solutions, or is a solution, or simply put, they can be regarded as solvents. Now they become acid. They become acids when they are introduced, when they are put into water, and by introducing them into water, they become aqueous solutions. Aqueous solutions, and these aqueous solutions, HCl, that has become acid, eventually dissociates. So they eventually dissociates, and in this case, it is a complete dissociation. So that's what actually makes them strong acids, because they completely dissociate to give their counterpart protein and chloride. Another example of an acid when put into water, a strong acid, is your nitric acid, your HNO3. Now, when introduced to water, becomes HNO3 aqueous. When it becomes an acid and an aqueous solution, and this completely also dissociates into the proton H plus and what? HNO3 minus. Okay, so note that strong acids do not have any equilibrium constants. Like we see earlier on, looking at the general acid-base chemistry, we began to see equilibrium constants. But for strong acids, they do not have any equilibrium constant, basically because there are no reactants that are left over as they completely dissociate with their component parts floating around in solution. So I like to note that down in red, worthy of note. So there are no equilibrium constants with strong acids. Please take note. Strong acids do not have any equilibrium constants. Do not have any equilibrium constants. Reason being that they basically do not have any reactants, have no reactants. They do not have no reactants that are left over as they completely dissociates with their components, as they completely dissociates with their components parts, dissociates with their component parts floating around in solution, floating around in solution. Their component parts floating around in solution. That's very key to note. Okay, they do not have any equilibrium constant. So we'll be looking at strong bases in the next slide. So we'll continue here with strong bases. Let me go back to my color of pen blue. So what are strong bases? What exactly are strong bases? Okay, so strong bases they are something like the strong acid. They are something like the strong acids, but instead of producing, okay, that's something like the strong acids, but instead of producing, all right, something like the strong acid, but instead of producing the proton, which is your hydrogen ion, okay, they produce the hydroxy ion. They produce the hydroxy ions. Thus, they completely dissociate when put into water as follows. Thus, they completely dissociate when put into water as follows. So, example of your strong base is your sodium hydroxide, your common salt. when it dissociates, it forms sodium plus your OH minus. So for strong acid, they produce the proton, which is your H plus, and for strong bases, they produce what? The OH hydroxide ion. So when they dissociate, there is none of the OH left. So you should just have a forward reaction. You do not have a reverse reaction. It do not have what? An equilibrium constant as well. So when they dissociate, there is none of the OH left. The only thing left to be floating around in solution is your NH plus and your OH minus. Okay, so that's basically it. Now we move to the important aspect, which are the weak acids and the weak bases. Weak acids and the weak bases. I want to do that in another slide. So we have the weak acids and the weak bases. Now, weak acids and bases do not completely dissociate when put into water. Simply put, that's how they are very different from the strong acids and bases. Weak acids and bases do not completely dissociate, do not completely dissociate when put into water. Okay, they do not completely dissociate when put into water. That's weak acid and bases. Note, the only thing that moves in acid-base reaction worthy of note is a basic thing you need to know in this whole acid-base reaction lecture. All right, and I want to note that down again in red. The only thing that moves around in acid-base reaction is the proton, which is the hydrogen ion. Okay, the H plus moves from one species to another species. The species that the H plus moves from donates or moves from, in other words, that's the species donating, is regarded as the acid, and the species that the H plus moves to, that's accepting the proton, is regarded as the base. Very important thing to note. So the only thing that moves in acid-base reaction is H plus, which is the proton. Very important to note. The H plus moves from one species to another species. Okay, so the species that donates the H plus is regarded as the acid. All right, while the species that accepts the proton or H plus is what regarded as the base. So the key word here is donates. The one giving out the H plus is the acid, and the one receiving or accepting the H plus is the base. So let's look at some examples of weak acids. Do this in purple. So we have weak acid. So the weak acid, an example, hydrogen fluoride, is a weak acid. When put in water, do not completely dissociate, so there's a forward and backward reaction. And what you have here is your H3O plus F minus. So you note that HF here gives out its proton. HF here gives out its proton to water. Okay, and that indicates that this is the acid, is the one donating the proton, and water is the one receiving the proton and is regarded as what? The base. So the acid is the one giving the proton and the base is the one receiving it. So another way to write this, especially in practical biochemistry, is this way. We have the HF, because water, it will always react in water. So you have the HF, and there you have H plus F minus. So this HF already is in aqueous solution, actually is in water. So we do not indicate the water. They are all in water floating around in solution. So HF gives out its proton to become H plus and F minus. Okay, so note that in this case, H plus is always attached to water to give H3O minus, which floats around in solution. Thus, H plus and HF are the same thing. So if we look at these two reactions, we are saying that H plus is always attached to water. It's always attached to water, and that gives your hydronium ion. Which is your H3O plus. All of these floats around in solution. As such, H plus and H3O plus are the same thing. Please note that they are the same thing. So it's either you see it as H plus as indicated here, or you see it as H3O plus. Also notice the equilibrium arrows. Notice the equilibrium arrows here, which shows it does not undergo complete dissociation. All of it does not dissociate. Okay? In fact, for weak acids and bases, most of the reactants do not dissociate in solution. So, because it does not completely dissociate, you must have an equilibrium, which is indicated by your forward and backward reaction. Thus, we can write equilibrium expression for this reaction. Next slide. So looking at that reaction, we want to writing an equilibrium reaction for the above weak acid dissociation. We have, okay, so I'll just write it on this page again so that you could see it clearly. So the last we wrote is HF dissociating in aqueous solution, dissociating forward and backward reaction, H plus aqueous plus F minus aqueous, all floating around in solution. So the equilibrium constant KEQ in this case is the concentration of the product, which is H plus, okay, over the concentration of the reactant. Okay, and this simply means this is actually equal to the dissociation constant of an acid, generally known as your acid dissociation constant. Okay, now if you look at this equation, this equation simply depicts the concentration of the product of a reaction divided by the concentration of the reactant. So there is a list of acid dissociation constants for different weak acids, such as hydrofluoric acid, as we have seen, phosphoric acid, etc. So for this particular weak acid, which is hydrofluoric acid, the concentration, the acid dissociation constant is this. So acid dissociation constant, acid dissociation constant for hydrofluoric acid is so you have acid dissociation constant HF is equal to 7.2 times 10 raised to power minus 4, and this number is a very, very small number. What's a very small number? And it implies that the H, okay, which implies that the H plus, which implies that the concentration of the H plus and F minus, okay, is a very tiny number. Is a very tiny number. And if the product, as it were, is very tiny, it implies that the reactant, which is the concentration of the hydrofluoric acid, is a huge or a very big number. This further implies that it is a very little HF that actually dissociates to produce the H plus in solution. Okay, so having HF here as a huge number further implies, okay, implies that a very little, okay, a very little HF, okay, was actually dissociated to produce the H plus in solution. Great. So is this thing an acid? Yes, it is an acid. Yes, it does dissociate, and the pH of the solution is going to be less than 7 altogether. It is a weak acid. It is not completely dissociated, and there is an equilibrium that takes place. So we're moving right along. We want to look at an example. in the next slide. So this will form our example 2. So we are looking at weak acid and bases, and we want to look at phosphoric acid. Phosphoric acid. Phosphoric acid is a very important weak acid in biochemistry. Very important to note. Phosphoric acid is a very important weak acid. It's a very important weak acid in biochemistry. Phosphoric acid dissociates, okay? So phosphoric acid which is H3PO4, okay? They dissociate and give up one hydrogen at a time, and give up one hydrogen ion. They give up one hydrogen ion at a time, having different expressions for each dissociation. Having different expressions for each dissociations. So we'll quickly just look at how they dissociate. So phosphoric acid, which is H3PO4, this dissociates in solution as a weak acid, releasing the first proton and leaving H2PO4 minus. And this forms the first acid dissociation constant 1. Now this H2PO4 goes back and reacts in solution to dissociate to form the next reaction. So we have H2PO4 undergoes a weak acid dissociation, releasing another proton at this time to form HPO4 2 minus, and that forms your Ka2, which is your acid dissociation constant 2. And thus last one still having a proton that could dissociate forms the third reaction, HPO4 2 minus. Okay, this should be minus here. 2 minus goes into a dissociation reaction to produce a proton plus PO4 3 minus, and that forms your Ka3, which is your acid dissociation constant 3. So let's take the second dissociation constant of phosphoric acid and look at what the equilibrium look like. So looking at this dissociation constant of the second reaction, we have in the next slide, okay, looking at the dissociation constant, acid dissociation constant, which is Ka2, will give us the product of the reaction, which is concentration HPO4 2 minus H plus, okay, over concentration the reactant, which is H2PO4 minus, and that gives a dissociation constant number of 1.38 times 10 raised to power minus 7. Again, this is a very, very small number. Okay, this is a very, very small number. Sorry about that. A very, very small number. Okay, so in the next page, we want to look at how this all works out. So writing out this equation, okay, let me just quickly put it out here again, which is Ka2 is equal to HPO4 2 minus okay, and we say this is 1.38 times 10 raised to the power minus 4. So writing out this explicitly using water as follows. You have so we'll continue from here, from our next slide. Thank you.